Hello, my name is Scott Milosek. I'm a consulting architect for BTA, Business Technology Architects, and I'm going to talk today about Precision Time Protocol, an IEEE standard for precise timing on a local area network. We'll discuss an overview of the protocol, describe which industries use it, and compare it to other network time protocols, and talk about how it works. In case you're curious, the painting on the slide that you see is called The Persistence of Memory. It was painted by Spanish surrealist artist Salvador Dali in 1931. I grabbed this painting because it seems to fit well with the topic at hand, time. So before we talk about timing protocols, let's understand what clocks are and why is accuracy and precision in clocking important. So clocks are just that, clocks. They keep time. And they keep time based on the vibration of a material. Usually it's quartz, but there's atomic clocks that are built around cesium and strontium. And recently, a clock has come out that's built around sapphire. So quartz crystals are typically used in any electronic device required to keep time, from your PC to your phone, your laptop, your iPad, whatever it is that you use, and it vibrates at exactly 32,768 times a second. While quartz is an inexpensive material to use to build the clock, it is subject to a phenomenon known as clock drift. This occurs because the method used to measure the time gets impacted and delayed by heat and age of the crystal. Over time, the clock can get out of sync with the actual time, and this can be problematic to several industries. We'll talk more about that in a minute. So for more accurate timekeeping, the atomic clock was developed. Most atomic clocks used atoms of the isotope cesium-133, and that vibrates at a ridiculous 9.1 billion times a second. So this isotope vibrates at a consistent and predictable rate and only experiences about 1 second of clock drift over 300 years. So it's very accurate. However, precision is becoming a factor in clocking and created the need for consistency between each vibration with no variance. The most precise atomic clock ever made was created by arranging strontium atoms in a grid-like pattern and then stacking those grids like pancakes. A newer, more precise clock mechanism has been created from a small, extremely cold crystal of sapphire. This was developed by Andre Luton when he was completing his studies at the University of Western Australia. Luton, the inventor, calls it the cryogenic sapphire oscillator. That's the picture here on the far right. It's currently in use and applied to an over-the-horizon radar used in Queensland, Australia, to detect illegal fishing vessels. This is a recent development effort, and Luton's company is now focused on reducing the size of that device. The challenge is the extreme cold that the sapphire has to be exposed to, which is 6 Kelvin, a few degrees above absolute zero. Let's talk a little bit now about why PTP. So many industries require accurate and precise timing. Finance is one industry, specifically stock trading. When a stock trade occurs, the timing of that trade has an impact on the value of the trade. Missing even 1 second of time while trading could potentially result in millions of dollars of losses, particularly for the large-scale trading houses. Manufacturing also requires precision timing to coordinate assembly line automation and for accurate measurements, precise placement and rotation of parts, and a myriad of other manufacturing processes that require precision. Telecommunications systems and video broadcasting environments require precise timing so that data, voice, and video can be streamed without delay, latency, or packet loss. Power distribution requires precise timing for protection, metering, and substation control functions. And finally, military, space, and defense systems must have accurate and precise timing. As we're sending people to the moon or Mars, we need to be sure that we know when to burn the engines and for how long to get the boost that we need to either get out of orbit or to slingshot around the moon to get back. And also, finally, we've got satellites traveling the universe, gathering scientific information for us, and we need precise timing on those devices as well, so that we can properly steer them to the target millions and millions of miles away. All precision timing applications require dedicated clocking hardware to ensure precision, and the network is no exception. So this chart is a comparison of time protocols, and it was recreated from an IEEE tutorial deck that was first published back in October 2005 by John Edison. So if we take a look at this table, we can see that the IEEE protocol was first created in 2002. And since then, there's been several updates, and we'll talk about those updates in just a second. The spatial extent of precision time protocol, IEEE 1588, is basically a few subnets. And the reason that you have that relatively small diameter network is to be sure that you continue to provide precise timing. The communications between the devices using PTP is a network, in our case, an Ethernet network. And because of the way the timing protocol works, we can get sub-microsecond accuracy in the context of timing. Now that is, or that does require that the local area network that you've built to support PTP is built on the IEEE 1588 design specifications for a communication network. We'll talk a little bit about that in another slide or two. The style used for synchronization is a master slave. So you'll have a master clock on the network where all the other clocks on the network derive their time from. It requires a very small computation footprint and very little network resources compared to the other protocols like NTP, GPS, TTP, and SIRCOS. And there is a latency correction for the network built into the protocol, and we'll actually talk about how that latency correction works. There is some security being developed around the protocol. The security is mostly focused on a keying mechanism to ensure authentication of both the master and the slave clocks. It's a self-organizing solution that only requires special hardware if you want the highest accuracy of precision in the context of your timing. And there's a few industries that actually do require that. As I mentioned earlier, the trading floors in the stock market typically have a dedicated piece of hardware whose sole responsibility is to provide timing on the network for the trades. And the update interval in the context of the protocol is about every 2 seconds. So let's talk about what is PTP. Well, so PTP was approved, like I said, back in 2002 by the IEEE, and there have been several updates for PTP since that time. And those updates include, as I mentioned before, security aspects that are being added to the protocol to help secure it. The protocol is capable of syncing multiple clocks on your network to within 100 nanoseconds of each other. And I'll stress again that That is provided that you've built your network according to the IEEE 1588 design specifications for this type of network. Now on the network, there are several types of clocks. There's the grandmaster clock and the slave clock. The grandmaster clock is typically the dedicated piece of hardware that uses GPS to get its time from the satellites in the sky and then provides that timing to its slave clocks. There are two different types of slave clocks. There's a transparent clock and a boundary clock. We'll talk about those in just a minute. Um, the protocol that is used is UDP for synchronization, and it's put out on an Ethernet packet. Supports both IPv4 and v6. We'll be talking about IPv4 in this scenario. And it uses multicast packets for the solution. I'll also point out that there is an SNMP v3 MIB that has been published as well for the protocol. So PDP uses UDP packets for the protocol to avoid the costly process of the three-way TCP handshake. There are specific UDP ports that have been assigned to PTP. You can see here there's the port 319 and port 320. 319 is an event port that is used when an event occurs, and 320 is the generic port. We'll talk about those ports in just a minute when we talk through how time synchronization works. Multicast packets are used on the network, so no IP addresses need to be allocated to the protocol. That saves a little bit of resources right there. Finally, the Ethernet packets have an ether type of 88F7, and that ether type is reserved specifically for the support of PTP on Ethernet networks. So PTP in the data center. So the network in the data center can support PTP, whether it's an ACI fabric or a standard three-tier core distribution and access layer. Now, I'll point out, though, that the ACI fabric, when it supports PTP, the spine has to be where the master clock connects in, and the leafs must be configured as boundary clocks. I'll also point out that from a VMware perspective, VMware started supporting PTP in their VMware 7.0 list, virtual hardware list 17. That's where you'll find the support for the products that VMware supports for PTP. In the context of ACI, PTP are only supported on second generation or later ACI switches. At the end of this presentation, I have a list of first generation ACI switches that do not support PTP for you to reference. If there's no external grandmaster clock connected to the ACI fabric, one of the spine nodes can act as the grandmaster. This spine switch has a PTP priority of 1 and a value of 254, and that's the default value. You can manipulate that so that when the clocks go through their election process to determine who the best grandmaster is, you can manipulate that process by using, for example, that priority value. The external grandmaster clock is mandatory for PTP in a multi-pod and ACI multi-pod scenario. Also, PTP operates only in boundary clock mode on the leaf switches. You cannot support end-to-end transparent or peer-to-peer transparent clock modes in ACI. And PTP is supported using UDP. It is not using Ethernet on the ACI fabric. PTP supports multicast communication only, and beginning with 4.01, support has been added to change the resolution factor to 11, which can then measure up to 214 milliseconds with an accuracy of 204 nanoseconds. So dialing in the precision here. And PTP must be enabled on all the leaves and spines within the fabric. Let's talk a little bit about the the network that PTP supports. So as you can see here on the right, we have a grandmaster clock, and that grandmaster clock in this scenario is a GPS board inserted in a router with an antenna that receives its clocking from satellites. That that device, the grandmaster clock, can then provide clocking to the boundary clocks here, the 1588 enabled boundary switches that are part of the fully compliant IEEE 1588 land architecture. And in that scenario, each of the boundary switches will receive its clocking from the master on a slave port that's connected to the network, the same network as the master is. The clocking for the switch is then synchronized with the master so that that switch can then provide master clocking to subordinate slave devices hanging off of it, for example, servers or manufacturing devices. So there's this is a high level view of what a typical IEEE 1588 LAN architecture may look like. We had mentioned earlier about how the clocks can synchronize and about how they have a function in the synchronization that accommodates network delay. So the synchronization occurs in two phases. It's a two-step clock. First, it obtains a clock offset correction, and then it determines the network delay. So in this example, the slave's clock starts with an offset of about 20 milliseconds from the master. You can see the master here is at 100 milliseconds. The slave is at 80 milliseconds. So there's a 20 millisecond disparity in the clock. The master constructs a sync message at the 100 millisecond time stamp to send to the slave. However, due to internal queuing and latencies, the message is actually sent and time stamped internally at 101 millisecond local master time. And then due to delays in the network, the slave doesn't receive the message until 2 milliseconds later at the 83 millisecond mark you can see here. After that message is sent, a follow-up message is sent shortly after by the master in this case, at 103 milliseconds. The follow-up message contains the previously timestamped value of 101 milliseconds in the message. This follow-up message is received 2 milliseconds later at the 85 millisecond local slave time. You can see here, 85 milliseconds. The slave then takes the 101 millisecond timestamp in that message and subtracts the previous timestamp value of 83 milliseconds, resulting in a calculated offset of 18 milliseconds. That offset is then added to the present time, resulting in a new clock time of 103 milliseconds on the slave clock. However, the master and slave clock aren't yet completely synced. There's this new adjustment hasn't yet accounted for the delay in the network. So this is where the second phase kicks in for time synchronization. The second phase determines the network delay. The slave sends a delay request message to the master at 108 milliseconds. The master receives and stores this message at 112 milliseconds local master time. A delay reply message is sent back to the slave with the time of 112 milliseconds. That's the time that the delay request was received. The slave receives the delay request at 115 milliseconds local slave time. The slave now can determine the network delay by subtracting the time it sent the delay request, which is 108 milliseconds, from the time the master received the delay request, which is 112 milliseconds, resulting in a value of 4 milliseconds. However, because there were two messages sent, that result of 4 has to be divided by 2, And so we get a 2 millisecond delay. The slave then adjusts its clock by 2 milliseconds to 117 milliseconds, and now it's perfectly in sync with the master clock. When using switches between a master clock and the slaves, runtime variations that occur in switches lead to inaccuracies in messages sent between the masters and slave. Given the switches save the received data packets completely and the queue effects they can be considerably long, the under certain circumstances, great fluctuations can occur here. At low network load, this may have little effect, but during times of greater network load, this can definitely affect time per synchronization. And this is resolved using Ethernet switches that are IEEE 1588 PTP boundary clocks. So these contain their own PTP instance where they operate as a PTP slave um, and are synchronized in relation to the connected master clock. For downstream PTP slaves, every switch port then operates as a PTP master and synchronizes the slaves with its internal time. This compensates all runtime fluctuations and wait times in the switches and enables the maximum accuracy to be achieved on larger Ethernet networks. And that's how PTP works. Thanks for your time. We appreciate you listening, and hopefully we'll talk with you later. Thanks.